Welcome to the wonderful world of physics. This is the beginning of chapter 23 on electrostatic energy and capacitors. In this video, we'll look at the first two sections, section 1 and section 2. We'll start section 1 on electrostatic energy, and I want to think about how we can use electric charges to store energy. You see this picture here, 3 positive charges. They don't have to be positive, but in this picture they are. And I've arranged them in an equilateral triangle just to make the math easy for this example. And I want to think about the potential energy involved in having them in this configuration. Now, the potential energy is the work done against the electric forces, the repulsive forces between them, when bringing them together. So if you bring 2 positive charges together, you know they repel against each other, and the closer you get them, they're pushing back, and so you have to do work against them. The work that you're doing is being invested. It's storing potential energy. So let's think about how much stored energy is there, assuming that they started out very widely separated, far enough away where originally they're not feeling a repulsive force. So imagine this is first a blank picture, and we bring in the first charge, Q1. Well, there's nothing there to repel it. It's coming onto a blank picture, a blank screen. So it takes no work to bring in the first charge because there is no electric field existing before it's there. Now, Q1 is there, it's present. Now think about the work it takes to bring in Q2. Again, assume that all of these are positive charges. We have to do work against that repulsive force from Q1. So we can say the voltage from 1, meaning due to charge 1, at location 2 is K times Q1 over A. That's the voltage from a point charge. So the work to bring in Q2 is Q2 times V1, so we're bringing Q2 into that location, and that becomes KQ1 Q2 over A. That's the work we do to bring in charge 2, and therefore that's the potential energy that's stored. Okay, we've brought in charge 2. Now let's bring in charge 3. To bring in charge 3, we'll say the work, W sub 3, is the work to bring it in against charge 1, so that's K Q1 Q3 over A, but we're also bringing it in against the repulsive force of charge 2. That's K Q2 Q3 over A. So it's following a superposition principle. Charge 1 is resisting it, and charge 3 is resisting it. So the work to bring in charge 3 is W2 plus W3, and we add them all together, and it's KQ1 Q2 over A plus KQ1 Q3 over A plus KQ2 Q3 over A. And again, the work is the stored potential energy. And then you can imagine, this is only 3 charges here. Imagine if we are adding more and more charges, 100 charges, 1,000,000 different charges, how much all of this would add up, the potential energy to bring them all together. The order of assembly doesn't matter. I could have done those in any order, it would still come out the same. You notice in the numerators, we have every possible combination of the charges. 1 and 2, 1 and 3, and 2 and 3. If the charges are positive or negative, then those values are included in the numerator. So sometimes if there's a negative and a positive charge, for example, that'll lead to a negative work done because it doesn't take any work to bring a positive and a negative together. In fact, it takes negative work to bring them together because they're already inclined to come together. They're attractive to each other. Let's look at one example. Calculate the electrostatic potential energy stored when 2 protons and an electron are arranged in an equilateral triangle, just as in the picture that I had drawn previously. And let's put them 1 angstrom apart. If you're not familiar with an angstrom, it's a term you should be familiar with. It's not an MKS, or it's not a metric prefix, but rather it is 10 to the negative 10 meters. It's roughly in the range of the size of molecules, 1 angstrom. So we've got these three charges, and you can see the potential energy formula that I previously derived. And we're going to think about these two protons and an electron. So here we have for the proton and the proton. Here we have for the proton and the electron. We'll say the first proton and the electron. And here we have for the second proton and the electron. So all possible combinations. Well, each of those terms becomes ke squared over a, negative ke squared over a, and negative ke squared over a. So in the end, the potential energy stored is actually negative ke squared over a. And so then we can plug in the values. There's k, there's e, we're squaring it, and there's a, the distance between each of them, 10 to the negative 10. All of this is done in MKS units. And we get negative 2.3 times 10 to the negative 18 joules. We can convert that to electron volts, negative 14.4 electron volts. Negative potential energy, which means there's no potential energy stored there. In fact, it's negative, meaning it didn't take any work to bring them together. You put two protons and an electron in this configuration, they will naturally come into that configuration. It actually takes work to separate them. Let's look at the next example. Same configuration, but three protons. So there we have ke squared over a plus ke squared over a plus ke squared over a, every combination of those three protons. And they all add up together and we get 3 ke squared over a. Plugging in the values, we get positive 6.92 times 10 to the negative 18 joules. We convert that, which gives 43.2 electron volts. So that's positive potential energy. And the positive means it took work to bring them together because overall it was a repulsive situation where they want to break apart, but we have to do work to bring them together. This brings us to section 23.2, which is capacitors. Capacitors are used for storing electrical energy. You can see some photos of some basic capacitor designs, and when we get to working with electric circuits, we'll play with some of them. But a simple setup for a capacitor is a parallel plate capacitor. It's two closely spaced conducting planes with equal and opposite charges. So you've seen this setup before in previous videos. Here we have a plate that has a positive charge Q, and here an oppositely charged negative charge Q. We're going to be doing math with these capacitors, so we'll just consider that each plate has some area. We'll call it area A. And notice the electric field. The electric field is a uniform electric field. It comes from the positive plate and goes into the negative plate. And by the configuration of these charges, the positives on one side, the negatives on the other side, there is storing of energy. Before I get into why that is, you can just imagine all these positive charges are lumped together in the same region. Remember, they're repulsive to each other, so it took work to get them all there. It also took work to get all these negative charges there. And so when you have to do work, as in the previous examples I showed, work to bring charges together, you've got stored energy. That's what a capacitor does. Now remember from chapter 22, where we went through the math of parallel plates, and we have from the positive plate, what I've drawn in dark blue there, the electric field goes from the left to the right, and it's sigma divided by 2 epsilon naught, where sigma is the surface charge density, epsilon naught is the permittivity constant. And then in purple, I've drawn the negative plate, and its electric field goes also to the right, sigma over 2 epsilon naught. So the net electric field is the two of those added together by the superposition principle. So the net electric field on the inside is sigma over epsilon naught, where sigma is the charge density, the surface charge density. So it's the charge Q divided by the area. which means that the net electric field is Q over epsilon naught and A. And remember, epsilon naught, the permittivity constant, is 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. And remember, this is where we get the Coulomb constant. When we do the Coulomb force, we use that K, and it's 1 over 4 pi epsilon naught. Now, the voltage difference between the plates is the electric field times the distance between the plates. So the voltage difference between them is the charge Q times the distance divided by epsilon naught A. Now epsilon naught, on the previous screen, I said that it's 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Now the units also work out, so the units are also farads per meter. So a farad is a unit of capacitance. And this comes about because epsilon naught is capacitance times distance divided by the area. And then we work it out that it's farads. Again, farads are the unit of capacitance times meters divided by the area, meters squared. So epsilon naught also becomes farads per meter. This equation in the box is your equation for a parallel plate capacitor. What is the capacitance? And when we go on in this chapter, we'll figure out, or we'll get into how we use capacitance in formulas. But for now, the capacitance of a capacitor is epsilon naught times the area divided by the distance. So it's based on the physical configuration of the capacitor, the size of it, the area of the plates divided by the distance. Let's think about how energy is stored in capacitors. And you think about how I started this video with bringing 3 charges together in a triangle. And it's going to be similar concepts here. So we've got these 2 parallel plates. And let's consider, start with the plates. Imagine that they're not charged in any way. They're just neutral. But we want to separate the charges so that we move a small charge, let's call it dq, from the negative to the positive plate. The change in potential energy as we move the charge from A to B is the work that it takes to move it from A to B. Now, practically speaking, this work is done by a battery. And the work done in moving a charge from A to B, remember, is Q times the voltage difference. Well, moving down here, that means that dW, the little tiny amount of work that we do to move that charge dq, is going to be V dq. And each additional charge increases the electric field, resulting in an increased voltage difference between the plates. So we can say that capacitance is charge divided by voltage. That's just a basic relationship between capacitance, charge, and voltage. And scaling this to our tiny charge elements and solving for Q, we can say dQ is C dV. So the work that we do in moving that tiny charge, instead of saying V dQ, is now V and C dV. Before I move on to the next page where my marker is, that's an important equation right there. Again, it's the basic relationship between the charges on plates, the voltage applied by a battery, and capacitance, that C is equal to Q over V. So remember this one right here. All right, so here we go. I showed the first half of this page I had on the previous screen. So if we're talking about moving a little charge, then dW, that little bit of work we do, is the voltage difference between the plates. And that voltage difference is set up by the battery. It has a certain voltage, times the capacitance, which is determined by the physical characteristics of the capacitor, times the little dV. Now each new charge increases the work needed to bring over the next charge. So the total work we do in bringing many, many charges over is the integral of all the little dW's. We're going to integrate, since we're integrating dV, we're going to integrate, we're integrating from 0 to the voltage, V is the voltage of the battery, times, and we're going to do VC dV. And I realize here I made a mistake. I'm going to write in, I moved the C out to the side, but there we go. There's my V. Okay. So the C is out to the side, and we're integrating V dV from 0 to whatever the voltage on the battery is. And so in the end, it comes out to be 1/2 CV squared. Well, these past 2 pages have just been the conceptual, the deriving the equation. The important thing here is, what is the potential energy stored in a capacitor? And it's this: the potential energy is 1/2 times the capacitance times V squared. Now, as I said, the capacitance is a characteristic of the capacitor based on its size and configuration, and that's something that's usually written on the capacitor in very small print. The V, the voltage, is going to be provided by the battery. That is the end of the introduction to chapter 23, and in the next video we'll get into using capacitors. Have a great day.